Yes. Hi everyone. So welcome back to Power Systems 2 online series. The title of the subject is Power Transmission System Design. So already we completed how we can calculate the resistance, inductance and the capacitance of transmission line. So now today let us we discuss about, that is unit 2, second unit, the performance of short and medium transmission line. Performance of short and medium transmission line. And before going to this unit, so what is short transmission line and what is medium transmission line? Short transmission line and a medium transmission line, and on what basis this transmission line is classified into short and medium like this. Let us we discuss this. And we know that the transmission line parameters are distributed parameters. What are the distributed parameters? Resistance per kilometer, inductance per kilometer, capacitance per kilometer. And we know that resistance and inductance are series elements for the transmission line. Therefore, the combination of resistance and inductance is considered as a series impedance of transmission line. Then series impedance of transmission. Then what about capacitance? The capacitance is shunt parameter. Shunt parameter in the sense, so this capacitance is exist between line to neutral, or in between line to line. So like that we have the effect of capacitor. So generally how we consider the effect of capacitance in the transmission line. So based on that, the transmission lines are classified into three categories. Those are short transmission line, medium transmission line and long transmission line. Yes, once again, so how we classify the transmission lines? The transmission lines are classified based on how the effect of capacitance is considered in transmission line. How the effect of capacitance is considered in transmission line. And moreover, the operating voltage and length also plays major role while classifying the transmission line. And if we see what are the various types of transmission line, that is, the first one is short transmission line. Next, second one is medium transmission line. And third one is long transmission line. Long transmission line. Short transmission line, medium transmission line, long transmission line. And let us see about short transmission line. Yes, when the length of an overhead transmission lines is up to 50 kilometers, that is short transmission line. Yes, when the length is up to 50 kilometers. Length is up to 50 kilometers, and the operating line voltage, that is the line voltage, is very low, so which is less than 20 kilovolts. 20 kilovolts. So then it is to be considered as short transmission. Yes, once again, what is short transmission line? When the length of an overhead transmission line is up to about 50 kilometer and line voltage is very low, that is 20 kilovolts, it is usually considered as a short transmission line. And here the length is very low and operating voltage is also very low. So hence what we can do in the sense, here the effect of capacitance are small and hence can be neglected. Yes, in the case of short transmission line, capacitance effect is neglected due to the smaller length and smaller voltage. The capacitance effect are small and hence can be neglected. Therefore, while we are analyzing or while we are studying the performance of the short transmission line, only resistance and inductance of the line are taken into account. So this is for short transmission line. Next, medium transmission line. Medium transmission line. Yes, medium transmission line. Yes, medium transmission line in the sense the length must be greater than 50 kilometers. That is, the length is 50 to 150 kilometers. 50 to 150 kilometers. Then operating voltage must be greater than 20 kilovolts. That is line voltage. That is 20 kilovolts to 100 kilovolts. 100 kilovolts. Okay. So therefore, how you can define the medium transmission line? When the length of an overhead transmission line is about 50 to 150 kilometers and the line voltage is moderately high, that is in between 20 kilovolts and 100 kilovolts, then it is considered as a medium transmission line. As the length is sufficient and line voltage is sufficient to consider the capacitance, so here we have taken we will take the effect of capacitance into account. As for the purpose of calculation, the distributed capacitance of the line is divided and lumped in the form of condensers shunted across the line at one or more points. So this is about medium transmission line. As in the case of medium transmission line, so we consider the effect of capacitance. So these 3 points you need to remember. Yes, what are the 3 points? The first one is the length is 50 to 150 kilometers and the line voltage is 20 kilovolts to 100 kilovolts, and here the effect of capacitance is taken into account. Yes, next, third one is the long transmission line. Long transmission line. Yes, long transmission line in the sense it must be greater than 150 kilometers because the medium is up to 150. So hence long in the sense greater than 150. Then what about line voltage? Line voltage is greater than 100 kilovolts. So therefore the length is greater than 150 kilometers and length voltage, operating voltage, that is the line voltage, is greater than 100 kilovolts. It is high. Yes, as usual. So the length is more, operating voltage is also more. Therefore here we must consider the effect of capacitance. effect of capacitor. So therefore, when the length of the overhead transmission line is more than 150 kilometers and line voltage is very high, that is greater than 100 kilovolts, it is considered as a long transmission line. Yes, for the treatment of such a line, the line constants are considered uniformly distributed over the whole length of line, and rigorous methods are employed for solution. As we will see what is rigorous method. This long transmission line performance will comes under the third unit. And second unit, in the sense the current second unit is so about short transmission line and a medium transmission line. Okay. Yes, so before going to the short transmission line, how we estimate the performance of the transmission line? Yes, how we estimate the performance of transmission line? There are two parameters are there. What are the two parameters in the sense? The first one is voltage regulation and second one is transmission efficiency. Yes, what are the two parameters to estimate the performance of the transmission line? Yeah, the first one is voltage regulation. VR stands for voltage regulation, and the second one is transmission efficiency. So first let me define what is voltage regulation and what is transmission efficiency. So now, what is voltage regulation basically? Suppose this is transmission line is there. At normal condition, it is having some voltage. Let it be some V dash. Whenever the line comes under to the operating condition, this V dash will goes to the V double dash. V dash as goes to the V double dash. That is, the change in voltage also affects the performance of the transmission line. That change in voltage so is to be considered as regulation of the voltage. So here when a transmission line is carrying the current, there is a voltage drop in a line due to resistance and inductance of the line, that is during the operating condition. So during the operating condition, the transmission line is carrying the current. So whenever the current is passing through the transmission line, as some resistance is present in the transmission line, some inductance is present in the transmission line, so therefore some amount of voltage is drop in the transmission line. When the voltage is drop in the transmission line, at receiving end, the voltage of the line is generally less than that of the sending end voltage. This voltage drop in the line is expressed as a percentage of the receiving end voltage and is called voltage regulation. So yes, once again, what do you mean by voltage regulation? Yes, when the transmission line is in operating condition, that means whenever the transmission line is carrying the current, so as some amount of resistance, some amount of inductance is present in the transmission line, so therefore some amount of voltage is drop in the transmission line. Due to this, at receiving end, the line voltage is less than sending end voltage. So it is represented as the percentage of receiving end voltage. So this is called voltage regulation. So usually, if suppose this is transmission line, the sending end voltage is represented by Vs and receiving end voltage is represented by VR. is represented by VR, and Vs minus VR, that is voltage drop. Vs minus VR, voltage drop in the transmission line. This voltage drop is represented in terms of VR, in terms of VR. So that is called voltage regulation, or we can also define, that is the general definition for voltage regulation, as the difference in voltage at receiving end of the transmission line between the conditions of no load and full load is called voltage regulation. The difference in voltage at receiving end. Yes, what is voltage regulation? The difference in voltage at receiving end of a transmission line between the conditions of no load and full load is called voltage regulation, and it is represent expressed in percentage of the receiving end voltage. Yes, that is given by that is percentage of voltage regulation. Voltage regulation, this is equal to, yes, what is the formula? Vs minus VR by VR into 100. Vs minus VR Vs minus VR divided by VR into 100. Okay, this is about voltage regulation. Next, the second performance parameter of transmission line is transmission efficiency. Transmission efficiency. Yes, basically what is efficiency? Efficiency is output power by input power. Efficiency is output power by input power. So here in the case of transmission line, what is output and what is input? So this is sending end power and this is receiving end power. So now what is output power? Output power is receiving end power and the input power is sending end power. So hence here efficiency of transmission system is equal to receiving end power. Output is receiving end power. Output is receiving end power and the input is sending end power. Receiving end power by sending end power. Into 100. Yes, now tell me now you tell me what is receiving end power? That is AC. AC power, AC receiving end power is VR IR cos pi r by Vs Is cos pi s into 100, where VR and IR are receiving end voltage, receiving end current, and cos pi r is the power factor at the receiving end, and Vs and Is sending end voltage and sending end current, and cos pi s is the power factor at sending end side. Okay, now you tell me, for good transmission line, efficiency must be high, regulation must be low. Efficiency must be high and regulation must be low. Okay. Yes. Now let us we see short transmission line, that is single phase short transmission line. Performance of single phase short transmission line. Yes, we know that in the case of single phase, that is short transmission line, in the case of short transmission line, we neglect the effect of capacitance. In the case of short transmission line, we neglect the effect of capacitance. Yes, now let us discuss about single phase short transmission line. Therefore, the performance indicates what we need to be considered. We need to be find out the voltage regulation and transmission efficiency of the single phase short transmission. So first, let us we model the single phase short transmission line. That is, let me take, because there is no effect of capacitance, the transmission line parameters are resistance and inductance, like this. The voltage here is Vs. So here I am connecting one load. This is R, this is L. The reactance of the inductance is XL, that is J omega L. XL is equal to J omega L R J 2 pi FL, where J is the imaginary part of the impedance, that is, which shifts the quantity 90 degrees in anti-clockwise direction. So let us assume this is sending end current Is, and here it is receiving end current IR. Let the voltage here is receiving end voltage VR, and here you can observe that this is simple series cycle. So hence what you can say, all elements are connected in series, therefore the current in all elements is same. So hence what we can say, in the sense, the sending end current is equal to receiving end current, that is equal to I. Sending end current is equal to receiving end current, that is equal to I. Yes. Okay. So now here, what is the drop in transmission line? Drop in transmission line is Vs minus VR. Vs minus VR. So hence here we can write as the sending end voltage is equal to Vs is equal, and if you apply the KVL for this loop, this is impedance of the transmission line, and here this is the load. This is Vs, and let it be this is VR, and here it is Z transmission line. So let the current is I. Now if you apply the KVL, yes, what is KVL? Vs minus VR is equal to drop, that is I into ZTL, or you can also write Vs is equal to VR plus I into ZTL. That is, you can rewrite this expression as Vs is equal to VR plus I into, what is the impedance of the transmission line? Impedance of the transmission line is R plus J into XL. R plus J into XL. Therefore, Vs is equal to VR What is VR? VR is receiving an voltage. Vs is sending an voltage. Next IR, I into R. I into R is resistive drop. Resistive voltage drop in transmission line plus J into IXL. IXL. So here generally we assume that the load is inductive in nature. Inductive in nature in the sense the load current lacks the load voltage. So here load current and line current both are same, because as all elements are connected in series, the current is same. Hence Is is equal to IR is equal to I. So therefore what we can say, the current I lacks the voltage VR. Here we can assume some angle. That angle is, let it be pi. Let it be pi. So therefore if I want to draw, just should remember these terms. VR, IR, J into IXL. Yes, first one is, so here I am drawing the phasor diagram. So first let me take the VR as reference. VR as reference. Then what is the current I? The current I lacks the voltage by pi. Lacks the voltage by pi. So let it be, this is current I lacks the voltage by pi. So here I want to find what is Vs. Next, VR already we have. Then what is one more term in Vs equation? Vs is equal to VR plus I into R. I into R in the sense resistive drop. Resistive drop is in phase with I only. That is, resistive drop is in phase with current only. Therefore, what you can say, the current made angle pi with VR. Therefore, I into R also made some angle, that is pi. This angle is pi. So here it is I into R. This is VR. That is VR. This is I into R. Next, what is the third term? J into IXL. J into IXL in the sense J term. So I already told, whenever any quantity is multiplied with the J operator, then that quantity shifted 90 degrees in anti-clockwise direction. So hence J into IXL in the sense this is like this. So here this angle is 90 degrees. Here it is I into XL. I into XL. Now if I club all these things, then it is sending in voltage. This is Vs. This is the phasor diagram. This is phasor diagram. Yes. Let it be, this is point O. This is point O. Let it be, this is A. Next, and here it is B. Next, if I extend this, then it is B. Let it be, this is C. This point is D and this point is E. Thus, what I have done in the sense, just I extend the I graph up to C. So which context, that means here I want to make one right angle triangle. That is, here I have ODC. OCD is a right angle triangle. So from this I want to find out the value of VR. Okay, so this is, let us we take the phase angles also, let us we differ. That is, the angle between VR and I is pi r, and angle between Vs and pi I is pi s. Just to see, angle between VR and I is pi r, angle between Vs and I is pi s. I hope now you have the right angle triangle. Yes, just to keep this. All of you draw this right angle triangle with A, B, C, D, E. A, B, C, D, E. So now from this triangle, I am deriving the expression for the regulation. Just to observe. Yes, so from right angle triangle, OCD. So what we can write? OC square is equal to OD square plus DC square. Right, sir? OC square is equal to OD square plus DC square. Now what is OC? From diagram you can see OC is equal to sending end voltage Vs. Now what is OD? OD is equal to, just to see that, OD is equal to OE plus ED. OD is equal to OE plus ED. Next, what is DB? Sorry, DC. DC is equal to DB plus BC whole DB plus BC. Okay, so now I substitute all these values in this equation, that is OC square is equal to OD square plus DC square. So just you substitute along with me, then this will be Vs square is equal to OE plus ED square plus DB plus BC square. Again, what is OE and what is ED? ED is resistive drop and BC is reactive drop. The ED is resistive drop and BC is reactive drop. So therefore we can write ED is equal to I into R, and BC is I into X. Then what is OE? OE is receiving end voltage that is OE can be written as receiving end voltage VR. It is not directly VR, it is VR cos pi r. And similarly, what is DB? DB VR sin pi r. VR sin pi r. Okay, now I substitute all these things in this equation. So then this will comes under that is Vs square is equal to VR cos pi r plus IR whole square and plus VR sine pi r plus ix whole square, ix whole square. So hence what is sending end voltage? Sending end voltage is equal to Vs is equal to root of this value. Yes, here we got sending end voltage. Actually, in your problems, the voltage represented is line voltage, that is receiving end voltage. So receiving end voltage, therefore you find the value of sending end voltage. Hence, what you can find? The first one is voltage regulation. You can find the voltage regulation, percentage of voltage regulation is equal to Vs minus Vr by Vr into 100. Next, sending end power factor. How you find sending end power factor? That is cos pi s. Yes, from the diagram, from the diagram, that is OCD. So from OCD, what is cos pi s? What is cos pi s? Cos pi s is OD by OC. OD by OC. Now what is OD? OD is VR cos pi r plus IR divided by Vs, that is OC. Next, what is sending end? What is power factor? What is power delivered? So power delivered is power delivered, yes, which is equal to VR IR cos pi r. Yes, here we find the three terms. The first one is voltage regulation, Vs minus Vr by Vr into 100. Next, sending in power factor, Vr cos pi r plus IR divided by Vs. Next, third one is power delivered, so which is equal to Vr IR cos pi r. Then what about the transmission line losses? Transmission line losses is equal to I square into R. So therefore, how much power sent? That is input power. Sending end power anacha, yes, power sent, let it be PS, sending end power, which is equal to VR IR cos pi r plus I square r, that is output power plus loss. Output power plus loss is equal to sending end power. So hence, what is transmission efficiency? That is power delivered by power sent. Receiving end power by sending end. Receiving end power in the sense VR IR cos pi r by VR IR cos pi r plus I square r into 100. This is the efficiency of short transmission line. Okay. and we will see the analysis in another way in next class. Yes, thank you for listening the class. So hopefully you got some information about classification of transmission lines. So today we discuss classification of transmission line and voltage regulation and transmission efficiency of short transmission line. Okay, thank you.